Everybody, this is example 1 for steel design of compression members. The problem statement that we have is a W12 by 50 steel shape is used as a column to support an axial compressive load of 200 kips. The length is 22 feet and the ends are pinned. Investigate the member for stability without regard to load or resistance factors. And here's our figure over here. It's a pin column. And the dotted line is just to give you an idea of the deflected shape. And the length is 22 feet. So the objective is to calculate the critical buckling load and compare it to the applied compressive load. And so the first thing we'll do is get 3 section properties, which is we get the cross-sectional area and the 2 radius of gyrations, and we can get this easily from part 1 of the manual for the W12 by 50 shape. W12 by 50. So the cross-sectional area is 14.6 inches squared. The radius of gyration with respect to the strong axis is 5.18 inches, and the radius of gyration with respect to the weak axis is 1.96 inches. So once we have these properties, we can calculate the slenderness ratio. And the slenderness ratio is equal to KL over R. And in our case, we chose RY, which is the smaller value. RY is smaller than RX. R sub Y is smaller than R sub X. So you choose a smaller R value because it will result in the largest slenderness ratio and hence result in the smallest critical buckling load, as you will see moving forward. So K is just the effective length factor. For a pin condition, it's 1, and the length is 22 feet, and we convert that to inches by multiplying it by 12 inches, and we divide it by R sub Y, which is 1.96 inches, and we get 134.7 as our slenderness ratio. Once we have the slenderness ratio, we can calculate the critical buckling load, and this is equal to pi squared times E times the cross-sectional area. E is the Young's modulus times cross-sectional area divided by the slenderness ratio squared. So we just plug in the numbers. Pi squared times 29,000 KSI times 14 inch squared is our area, and divide that by the slenderness ratio, 134.7 inches, and we square that value. Oh, excuse me, the KL over R, the inches shouldn't be there. This is a unitless value. So you can cross that out. So it's just 134.7, and we square that. So the critical buckling load that we obtain is 220.8 kips. So since the applied load of 200 kips is less than the critical buckling load of 220.8 kips, we can say that this column is stable. And also we can calculate the safety factor, and we do that by just dividing the critical buckling load by the applied load. So this is equal to PCR divided by P applied. So 220.8 kips divided by 200 kips, that gives us 1.1, which is our safety factor. And this is the end of example number 1. Thanks.